We have 1 more minute maybe before we start. All right, well, let's start. So we've got a good number of people here. So welcome to the second seminar of the online nuclear reaction seminar series. Today we've got the pleasure of hearing from Kyle Brown at Michigan State University. But before, let's do some housekeeping. So in case you weren't at the last meeting, my name's Caitlin Cook. I'm an assistant professor also at Michigan State University. So today we have a few items. The first is to remind everybody of the existence of our website and our mailing list. That's the best way to get details of meeting announcements and meeting links. The second is on our website you can find recordings of our seminars, just in case there are colleagues of yours who are interested in these talks that have missed it. So you can find Mario Gomez's talk by going to the schedule and clicking his name. I think Jin is going to put a link on the chat for you. So we will be recording the seminar. Last time we didn't record the questions because we didn't inform people that we're recording. This time, if there is an objection to questions being recorded, we can remove that as well. But otherwise, I think we'll include the questions this time. The last item, also about our schedule. As of next week, we will be having seminars on Tuesdays and Thursdays, thanks to everybody who signed up to give a talk during this time. So every Tuesday and Thursday it will be at 9 AM, apart from next Tuesday when we have a special time at 9:30 due to our colleague being on the west coast of the US. Lastly, about questions. So because we don't want everyone to be unmiked all at once, we're going to be keeping everybody muted unless they raise their hands. So you can, if you want to ask a question, please raise your hand. You should find it in the bottom bar that controls the meeting. If you can't work out how to raise your hand, or if you have some kind of problem, please just say, I want to ask a question in the chat. And one of the co-hosts will be keeping an eye on that and will let you ask a question. Although we're going to generally request that people keep questions to the end. If you have an extremely urgent question that just can't wait, please raise your hand during the talk or put something in the chat. So with that, let me introduce Kyle. So Kyle is an assistant professor of chemistry at Michigan State University, as well as the Facility for Rare Isotope Beams. So he completed his PhD in 2016 at Washington University in St. Louis on the study of 2 proton decays from ground states and isobaric analog states. His PhD work was awarded the Dissertation Award from the Division of Nuclear Physics of the American Physical Society. Before he was an assistant professor of chemistry at Michigan State University, he was a P. Gregers Hansen postdoctoral fellow at the National Superconducting Cyclotron Laboratory until 2019. So moving on from 2 proton decays, his research now focuses on the nuclear equation of state through heavy ion collisions and nuclear structure observables. And that's what he's going to be telling us about today. So Kyle?
Okay, can you hear me?
Yeah, we can hear you.
Okay, great. So thanks everybody for coming. Good morning, good afternoon, good evening, wherever you are around the world. And also thanks to the organizers for giving me the chance to speak. It's nice to still have seminars during this rather unusual time. So today I'm going to be talking a little bit about the work we've been doing over the last sort of 2 years at the NSCL and FRIB, and I'm going to talk about how we can go about constraining the parameters of the equation of state using these heavy ion collisions. There we go.
Sorry,
okay.
Kyle, just to interrupt you before you get going. Could you put your camera on, please?
Yeah.
If that's okay.
I thought I did.
Oh, maybe, okay. I'm just incompetent. I'm sorry.
Okay.
All right.
Great. So, oops. So my my outline is here. I'm going to talk a little bit to start with about equations of state in general, and also the nuclear equation of state. What is it, and why do we find it important? And then I'm going to talk about how we go about constraining that equation of state through experimental science. both at and below the saturation density as well as above the saturation density. And then I'm going to talk about a specific aspect of it, which is the nucleon effective masses, what observables that they're sensitive to, and how can we go about measuring these observables. And then I'll talk about our experiment and our results, and then at the end, if there's time, I'll talk about how we can extend these measurements into the supersaturation density using the new FRIB facility. Okay, so what are equations of state? Well, I think familiar with equations of state through chemistry. These are thermodynamic relationships between variables like the temperature, pressure, and density of fluids and other matter. Most common ones you would come across are something like the ideal gas law, where if you can describe how the pressure and temperature of a system will change if you squeeze it or expand it. In the nuclear realm, we have to deal with this equation of state with finite nuclei, but also very exotic systems like you'd find in a neutron star with nuclear or nuclear neutron matter. But it's on a very different density scale. So if you think about everyday densities like liquid water, for instance, it has a density of 1 gram per cubic centimeter, whereas in the nuclear regime, we're dealing with something that is 14 orders of magnitude larger. So it's a very different problem in general. And it's also different fundamental forces that are at play. So the nuclear equation of state is nothing new. We're trying to express the properties of these compact nuclear objects using what we know about thermodynamics. And this has been done since near the beginning of nuclear science. The first sort of attempts were made with something like the liquid drop model, which worked really well for things like stable nuclei, where we can write out their binding energy as a function of things like their bulk binding, and then make correction terms for the fact that there's a surface and part of the nucleons are charged. We had to take into account what happens if you have an imbalance in the number of neutrons and protons. And also we had to add in shell effects. And so all of these things add in correction factors. So what we're going to do with the nuclear equation of state is add in a few more of these correction factors when we move away from things like saturation density and we move away from beta stability. So these are the kind of things that we're trying to assess today. If we want to talk about the density dependence, this is really important because we know that nuclei are not incompressible. And so the density needs to be allowed to vary in this equation. If you think about a neutron star, for instance, a neutron star has a whole range of densities inside of the star itself. And so we need an equation that'll work for the whole range of densities, both below and above this typical nuclear densities. And so for symmetric matter, we have an equation of state that is something like this. It has the most binding near the saturation density, and then it becomes less bound as you move away, as you either expand or compress the system. This minimum has been set by measurements of the giant monopole resonance and has been known for quite some time. If we want to talk about things like neutron stars where you're in a very asymmetric system, we need to add in another term called the symmetry energy. This is the term that pulls in the binding energy as a function of this asymmetry, this difference in the densities of the neutrons and protons in that system. And right now, this is the largest uncertainty we have in the equation of state. And it's basically the cost you pay for having an imbalance in the number of neutrons and protons. And as a function of density, that's basically this gap between the equation of state for symmetric matter and the equation of state for pure neutron matter, which is never bound. So what we're trying to do is find out how large is this gap as a function of density for the whole range. And as I said, it's really the most uncertain part of the equation of state right now. It's the part that I think most people are really working on. And what you often do when you don't know the functional form, let's say, of something is you write a Taylor expansion about some place where you know something. So what is often done for the symmetry energy is we write it as a Taylor expansion around the saturation density, rho 0. This is the saturation density is the density in like the center of a lead nucleus, for instance. It's that central density. So what we really need to do then is to constrain these parameters in this Taylor expansion. So we're looking to try to constrain like the slope and the offset in this expansion. And then there are higher order terms like the curvature and so forth, but those are less certain and often neglected. And these parameters have been constrained by a wide variety of experimental inputs. We've constrained them through measurements of nuclear masses and isobaric analog states, measurements of the electric dipole polarizability of a nucleus. But really, the focus I'm going to make today is on heavy ion collisions, because right now, this is our only terrestrial tool for studying things at this equation at both high and low density, because basically we can tailor the density region by just changing the beam energy of our projectiles. So it's a really useful tool, and it's what we're going to focus on today. And really, the equation of state is one of these things that has a wide-reaching impact on lots of areas of nuclear science. It plays roles in nuclear structure. It can determine things like their masses and positions of isobaric analog states. It also plays a role in determining how thick the layer of extra neutrons is on heavy neutron-rich nuclei. It obviously plays a large role in nuclear astrophysics, in neutron stars being the most, I think, prolific example. It plays a role in determining their mass-radius relationship. It talks about cooling rates and their tidal deformabilities and all of these things. It also goes into talking about how neutron stars merge and also the R process. And then in nuclear reactions, which is the focus today, it also plays a role in how these collisions progress, the particles that come out of them, and things like that. In neutron stars, I think are sort of the most interesting system to study with the equation of state, because it's a really rich playground for it. You have throughout the whole part of the star, you have lots of different density regions. In the sort of outer regions of the star, you have this lattice of finite nuclei surrounded by a neutron gas. It's a density that's lower than the saturation density. And here, the equation of state plays a role in determining things like where the crust core transition density takes place. It plays a role in forming nuclear pasta and the frequency of star quakes. And then as you move deeper into the star, gravity is compressing things, the density increases, and really you're dealing with neutron-rich nuclear matter. And so in this region of the star, this is the region that's has the biggest role to play in the compactness of the star, the mass to radius, mass over radius. It also plays a role in things like the moments of inertia stars. And as we move even deeper, there's much less certainty, and so I won't talk about that. And so really what we need to do is we need to know the equation of state at both this high and low density regions to really understand these interesting astrophysical objects. So there's a lot of work being done from a lot of different angles. So one of the more interesting experiments that's being done at Jefferson Lab is to try to measure this extra layer of neutrons on the surface of these neutron-rich heavy nuclei. They had a first attempt some years ago to measure this using parity violating electron scattering. They were able to measure this with a rather large error bar. They have, I believe, just wrapped up their new experiment to shrink this error bar both in the systematics and the statistical uncertainties. And so if they can really place a tight constraint on the neutron skin thickness, this directly correlates to this slope of the symmetry energy at saturation density. So it can provide a really nice constraint if they can shrink down those error bars. And the number here on the plot is not representative of what they've measured. It's just some prediction of what their new uncertainties would be. I haven't actually seen the new result if it's out yet. Okay, another interesting and new way of looking at the equation of state is actually taking it from astrophysics directly. So almost 3 years ago now, the the LIGO collaboration measured for the first time the merger of two neutron stars. And this actually allows us a really unique window into the equation of state, because really what you're measuring is almost pure neutron matter. Neutron stars are almost entirely neutrons. And so if they can measure observables that are sensitive to this equation of state, something like tidal deformability, they can provide tight constraints on this equation of state. And so what they were able to release from that first measurement is this blue band, is a pressure as a function of density. And so this blue band really represents the pressure of nearly pure neutron matter. And then some years ago, there was really tight constraints placed on the symmetric matter equation of state from kaon production and also elliptical flow measurements. And from those two, if the symmetry energy is really the difference between symmetric matter and neutron matter, you should be able to just take the difference between this blue curve and one of these colorful boxes, and that should give you your symmetry pressure as a function of density, or the symmetry energy. The issue is that the error bars on both of these measurements are rather large at the moment, and so what you end up getting is something that's not very certain. So it provides a rather loose constraint, but I think in the coming years, we should be able to shrink the error bars on the neutron matter side from further measurements of neutron star mergers, and perhaps from something like a neutron star black hole merger. That would be very interesting. But also we'll be able to shrink the error bars on the symmetry energy that we measure from heavy ion collisions. So we're attacking this problem from lots of different angles. Okay, so one observable that often gets not talked about very much is the momentum dependence of the symmetry energy. We talked a little bit about the density dependence. That's something that gets focused on quite a lot. But you also have in these nucleon potentials momentum dependent terms, which are natural inside of this potential. And so these momentum dependent interactions lead to an apparent reduction in the nucleon mass. So this is often called the effective mass. In the symmetric matter equation of state, these effective masses are something like 70% of the free neutron mass. But if you move into the asymmetric matter, these potentials that are felt by the neutrons and protons can be different, and this can lead to a splitting in the effective masses of the neutrons and protons. So what we're trying to do today is to constrain this quantity, the difference in the effective mass of the neutron and proton for neutron-rich nuclei. The literature on this is a little bit murky because often people don't label exactly what they're talking about. So there are a lot of different ways of describing this effective mass. I'm using the effective masses of the neutrons and protons, the difference in them. But this is also equivalent to saying the isoscalar and isovector effective masses. They're related in some relationship like this. And they can be constrained from a lot of different observables. So if we want to talk about the effective masses for things at or below saturation density, these have been looked at in optical potentials. So the depth of this optical potential is sensitive to these effective masses. If you were to reduce this effective mass, this is basically the same as adding another repulsive term to your potential. And so the depth of these optical potentials is sensitive to this effective mass. And these, for instance, the isovector effective mass is quite important. It affects the heat capacitance of neutron stars and protoneutron stars. And so this goes into affecting their cooling rates through things like the Urca process and modified Urca process in cooling of neutron stars. So this plays an important role in other ways inside of neutron stars as well. You can also constrain this at higher densities from observables like elliptical flow. I'm going to talk about this at the end, so I'll skip it for now. For the isoscalar and isovector effective masses, you can also constrain these at saturation density from nuclear structure observables. So these have been constrained in the past by measuring the position of the isoscalar and isovector giant quadrupole resonances. And these are both sensitive to the isoscalar effective mass for the isoscalar quadrupole resonance and same for the isovector. But what is sensitive to this neutron proton effective mass splitting? So one of the thing I'll talk about today is the ratio of neutrons and protons emitted in a heavy ion collision. So this is what the observable we found to be sensitive to this effective mass splitting. And the nice thing is it's sensitive to this effective mass splitting both above and below saturation density. So it's an observable we can use across a wide range of scattering energies. And it's an interesting quantity in its own right. It affects things like the equilibrium ratio of neutrons and protons in the Big Bang. It affects things like the neutrino opacities in supernovae and in neutron stars. And it also goes into affecting level densities. And so what can we do with heavy ion collisions to really constrain this? Well, I'm going to walk you through this plot. It's a little bit complicated. This is calculations from IMQMD. It's a transport model code of collisions of 10112 and 10124 at 120 MeV per nucleon. The plot on the right is, sorry, on the left is a plot of the ratio of the yield of neutrons to the yield of protons as a function of their kinetic energy in the center of mass frame, and for a number of different Skirm potentials. So all of the red curves you see have chosen the effective mass of the proton to be larger than the neutron, and all the blue curves have been chosen for the effective mass of the neutron being larger than the proton. And we see that, especially for the neutron richer system, there becomes a sensitivity to this this parameter, especially at large kinetic energies. And so, what we think we can do is if we can measure this this yield ratio, we should be able to determine the effective mass splitting using this observable. Why does this make sense? Well, if your effective mass of your proton is larger than your neutron, if the effective mass of the neutron is smaller, if you think about an F equals ma, then your acceleration is larger for the same force. And so this goes into having more neutrons at higher kinetic energies because they're basically feeling a larger acceleration, and vice versa for the other ways. And so this becomes a rather nice observable for trying to tease out this effective mass splitting. The difference between the open and the closed circles, or call it in dashed lines, is the effect of changing basically the slope of the symmetry energy. And so we see that while it does play a role in also determining this ratio, it's a much smaller effect on the overall ratio. And so if we were able to measure this for a whole series of systems, we should be able to tease out the two contributions, both from the density dependence and also from the momentum dependence. The plot on the far left, or so the far right, is the double ratio, where we take the ratio of neutrons and protons for the neutron-rich system and divide it by the neutron-poor system. This is done because it is a nice thing for the experimentalists, because often if you don't exactly know your efficiencies to the highest precision and other effects, this is a nice way of canceling them out so that you don't have to worry about these too much. And so we can still see some sensitivity to these effects. And so we're going to use the double ratio because it's just a little bit more convenient. So this has been done in the past. There is some work from our group back in the mid-2010s where we looked at collisions of 10 on 10 at 120 MeV, just like the calculations I was showing you. The data is shown here in black with associated error bars, and then the calculations are here in red and blue, where again, the red is where the effective mass of the proton is larger, and the blue is where the effective mass of the neutron is larger, the neutron-rich nuclei. And we see that the data sort of just begins to maybe hint towards the neutron effective mass being larger, but the error bars are large, and the data runs out right where we start to get interesting, where the curves start to split apart. And so we want to try to go about improving this, picking a different system, and also trying to improve at the same time both our dynamic range for these particles and also our we'd like to upgrade our understanding of these experimental systems so that we can better cancel out these systematic uncertainties. So we did just that back in 2018, March of 2018. We measured about 16 different beam target combinations. We measured systems of calcium on nickel, both neutron-rich and neutron-poor on 2 different nickel targets, and we also measured a very asymmetric system of calcium on tins. The calcium on nickel systems are really nice because they are rather easy and reliable to calculate with transport models. They don't take a lot of time to do these calculations, and so we can use them as a way of really very quickly getting out some physics information. Whereas the calcium on tin, they have a larger asymmetry. They should be more observable to the momentum dependence, and they should also be sensitive to the participant dependence on the nuclei-nuclei interaction. So we're going to use all of these things to try to better constrain both the density and momentum dependence of the symmetry energy. And we made a lot of improvements over the previous work. We developed a new charged particle veto wall that now fully covers the neutron walls with no gaps, and it has really good spatial resolution, so we can remove charged particle backgrounds from our neutrons within the same event. And at the same time, we also upgraded our charged particle detectors. We've increased the cesium iodide crystals in them from 4 centimeters to 10 centimeters, effectively doubling the range of proton energies that we can measure. And so we're, with both of these improvements in mind, we went about measuring these systems. These are some pictures from the experimental campaign. Inside of this ball of cesium iodide called microball, we had our targets on the target ladder. The microball was used both as a trigger for the system, but also as a multiplicity measure where we can actually constrain the impact parameter of the collision. So we can basically fine tune whether we have a central or peripheral collision in the data. And then we had several different detector systems. The first is HIRA. This is a set of silicon cesium iodide telescopes. It has very nice position and energy resolution properties. And this is where we have these longer crystals where we can measure high energy protons now. For the neutrons, we measure their energy by time of flight. We have a small array of plastic scintillators here as our start detector for the time of flight. And then inside of these large metal boxes are 2-meter long, 8 centimeter square bars of liquid scintillator. There's about 50 bars that we can use to measure neutrons with about 10% efficiency for each wall. These bars here you see are the veto wall. It was constructed by Western Michigan University, and it's used to basically veto out the charged particles we have. Okay, so moving into the data, we had, this is the charged particle data. So this is coming from HIRA itself. I'm plotting the, basically the momentum, transverse momentum as a function, or divided by a nucleon number as a function of the rapidity in the beam frame. So this is the rapidity scaled by the beam rapidity. So at 1, it's the same velocity as the beam. And this is done for all of the hydrogen and helium isotopes, protons, deuterons, tritons, and then the heliums here. The top row is all of the raw data. And you can see you have a lot of structure in it. This is because in HIRA, we have basically 3 towers of detectors and each one of these bands corresponds to one of those towers. And so what we're going to have to do is correct for the fact that there's a lot of gaps in those towers in total coverage. There's a wide varying in the amount of pixels per solid angle, and so we need to correct for that. We also have to apply corrections for the fact that as these high energy protons and other charged particles are moving through the cesium iodides, they can undergo nuclear reactions inside of those cesium iodide crystals. They can produce gammas or neutrons. And all of those reactions cause energy loss, and those particles are then basically lost to us. We can't cleanly identify them as a proton or a triton, for instance. And so we have to also make a correction factor for that. We believe we've done that. That is down here on the bottom. These have been corrected for both efficiency and reaction loss. This is courtesy of one of our postdocs in the collaboration I mentioned. And so we now have these corrected charged particle spectra, and so we're ready to go on that side. On the neutron side, we have done quite a bit of work. All of calibrations have been done. This is work by one of the graduate students, Xuquan. They've been calibrated for their energy and timing, position, and we've also implemented and developed a new method for doing the pulse shape discrimination. This is to try to better distinguish between neutrons and gammas inside of these long bars. The result of that you can see on the right here. We have really nice separation between the neutrons and gammas in these bars. And so if you're interested in that method, I don't have time to talk about it today, but we can talk about it at the end if there's a question. And that's been submitted to NAM, so look forward to that. We've also implemented a new vetoing algorithm to try to remove these charged particle backgrounds, and I think that's been rather successful. We've also, during the run, we have about half of our data with shadow bars in place. These are long bars of basically heavy met that can shadow out any particles going through them, so we can get a better handle on our neutron scattering background. So we think we've done a nice job on that too. Really, the last thing we're waiting on is, we're not waiting on it, but it's taking some time, is determining the detection efficiencies, because these are, for the neutrons, they are energy dependent. As different energy neutrons interacting with the liquid, different reaction channels open up, and so these have to be taken into account in a very accurate way. And so we're still working on this, and it's not quite ready yet. So I won't actually talk about the neutron data today. So if I don't have neutrons, how am I going to go about taking a neutron-proton ratio? Well, it turns out there's another way to do it without worrying about the neutrons at all. So I'm just going to look at the charged particles and try to construct a neutron-proton ratio from them alone. So I want to construct this sort of pseudo-neutron spectrum. The way I'm going to do that is from the T-helium-3 ratio. If you think about a triton, neutron and a proton, a helium-3 is a neutron and 2 protons. If I divide their spectra out and multiply it by my proton spectrum, I get something that should resemble the neutron spectrum in these reactions. The tricky part comes in the fact that our detection regions for protons and tritons are very different. Tritons have a much larger range, and so we're not going to be able to go up as high in energy by measuring the tritons, because basically they punch through our detectors much sooner than the protons. If we look at the proton spectrum, we need to find a region for which the detection over the whole cut is basically 100%. We don't want to be down here in a region where we have data in some part of the cut but not in another. So we have to set some sort of lower bound on our momentum, transverse momentum. And similarly, on the upper region, we have to also set a cut, because at some point the protons will punch through, and we have to throw away those protons as well, because they're not cleanly detected, and so we don't want to include those in our ratio. For tritons, this is much more limiting. not so much on the lower end, but on the upper end, because the punch through is just so much slower. So that will be a limitation for us in determining the neutron-proton ratio. We won't be able to go out as far as we like until we really get the neutron spectrum. And we're also placing a cut on the rapidity to try to look at particles basically coming out at 90 degrees from the reaction. I'm looking in the rapidity frame rather than in, say, like the energy in the center of mass, because I'm looking at calcium on nickel systems. And if you look at calcium 48 on nickel 64 versus calcium 40 on nickel 58, their center of masses are different. And so getting a combination of those two systems together is a lot more of a headache than it is dealing with something that's invariant of the PT. So that's the only reason for that. The other thing I'm going to do is I'm going to break down all of the clusters that we measure into their constituent neutrons and protons. So for instance, if I look at the helium-3, it's made up of a neutron and 2 protons. So I'm going to add it into the spectrum for the neutrons and the protons, twice to the protons and once to the neutrons, because in transport model theory, the cluster production is not often done very well. And so just to make a very clean comparison, we're going to break down the clusters in both the data and the theory to try to do a really clean comparison. Okay, so what does that look like? So the data are shown here in black. This is, again, the double ratio. I'm taking the ratio of the neutron-rich system, calcium 48 on nickel 64, and dividing it by the neutron-poor system. And that's shown here as the dots. And then I have my two, again, IMQMD calculations using 2 different Skirm parameterizations. And you can see, again, we're right at the region where the data is sort of giving us a sense that for the blue, which is for the neutron mass larger than the proton mass, effective mass, that it's starting to favor that. And actually, the data is a little bit more favoring that than what we saw in the 10-on-10 collisions. But really, we need to get to the neutron, the real neutrons, because we really want to push this out to much larger region, because really the separation is becoming much larger. And really, so we're really waiting on the efficiency correction for the neutrons. And in the end, all I've done here is I've just chosen 2 particular Skirm interactions. That doesn't really matter which ones I choose. I just chose my favorite, and I plotted them on top. But that's not a really fair comparison. What we really want to do is what we've done in the past for the 10-on-10, where we take a Bayesian approach and really try to look at all of the different systems together with both the single and double ratios to really try to, in one consistent way, constrain both the density and momentum dependence, because they are correlated, and just because I've chosen this particular Skirm interaction doesn't mean it's doing a good job at constraining both of these parameters. So we're going to try to map out the whole parameter space. And I also want to look at going to other observables that are also sensitive to this, so that I can have another window into these parameters. So the way I'm going to look at that is through the elliptical flow. Looking into the future, the NSCL, the National Superconducting Cyclotron Lab here at Michigan State, is closing down. We have about a year left on the schedule, but we're making way for the facility for rare isotope beams. It's scheduled to be completed in 21 or 22, and it's well on the way. And the nice thing with EFRIB is it's really going to be able to extend our reach to the both high density region and also the larger asymmetry region. So for most beams, the EFRIB will be able to provide up to 200 MeV per nucleon. I just chose an example here, 10132. We should be able to get at 200 MeV per nucleon more than 1 million particles per second. This is more than we could ever want. And so we'll be able to do really nice experiments with rather neutron-rich beams in just a few years. And so we're going to try to do the same kinds of experiments that we're doing now and extend them out to a much larger density. And in the far future, we have left space in FRIB's design to extend the energy range up to about 400 MeV per nucleon. So we'll be really able to push this density region even further in the future. As well, we're also building a new spectrometer in FRIB. It's called the high rigidity spectrometer. And we'll be able to move the spirit time projection chamber from where it is in RECAN now to FRIB to also measure more observables that are sensitive to these parameters with FRIB in the future. So that's something that we're preparing for and we're looking forward to in the future. This is where the slide went. So the other observable that we're going to start looking at is something called the elliptical flow. It's been looked at in the past by lots of groups. It basically is the anisotropy in the emission of particles coming out of the plane and inside of the reaction plane. So the amount of particles coming out here versus the amount of particles being emitted inside the reaction plane. And the magnitude of this V2 parameter really is sensitive to the pressure inside of this essential region of this collision. The nice thing with this parameter, this V2 parameter, is it's not only is it sensitive to the effective mass shown between the red and the blue again, but it's sensitive all the way out to 400 MeV per nucleon. So we'll be able to use this observable far into the future with FRIB to also be able to constrain this momentum dependence. So with that, I'd like to summarize. We're really looking for input from transport model codes to really constrain this neutron and proton effective masses by comparison to our data. And the observable that we have found that's very sensitive to this effective mass dependence is this neutron-proton ratio in heavy ion collisions. We've carried out this experiment, and we're at the sort of 5-yard line. We're almost there with the neutron spectrum, and so I think within the year we'll have the first physics paper out on the actual neutron-proton spectrum. Preliminary analysis with the charged particle data alone is really pointing to the effective mass of the neutron being larger than the proton for these neutron-rich nuclei. But we really need further simulations and really Bayesian analysis to really precisely determine this neutron-proton effective mass splitting. So I would say stay tuned to try to see what this effective mass splitting actually is. This work is a large collaboration with several different universities around the world and a large number of people that are, there's so many to thank. But with that, I would like to thank not only them, but you for attending.
Great, thanks very much, Kyle, for a really enlightening talk. It's a shame that applause just doesn't work over Zoom, so we're quite sure how to do this.